All right. So welcome again to the Murray Amateur Radio Club. We're going to talk tonight about attenuation. And this is a very brief attenuated class. I only have like 15 slides, so we should be able to run through this fairly quickly and leave a little time for discussion. But again, if you do have questions or comments along the way, feel free to sing out. When we get this posted, you can also comment on the website if you have a account on our club website. So
Even the number of slides is attenuated.
even the number of slides is attenuated. That is correct. Yes. All right. So attenuation. What is attenuation? Well, according to Merriam-Webster Dictionary, attenuation is a noun, and it is the act or process of attenuating something. Well, that really helps us, doesn't it? Yeah. So, or the state of being attenuated. So I love it when definitions do this because it's like, oh, well, what's a table? Well, it's a thing that looks like a table, right? So it's wonderful when they do this. But the idea is that it has three definitions essentially: a lessening in amount, force, magnitude, or value, a reduction of severity or virulence, as in a decrease in the pathogenicity of a microorganism. Try to say pathogenicity 10 times of a microorganism, or in the severity of a disease, or a diminution of thickness. Now, the other definition that I looked at had a slimming down as the first definition. And I was like, well, I don't want to use that because I'm not slimming down, and I don't think anybody in here is slimming down. But the one that we are talking about is a lessening in amount, force, magnitude, or value. So when we're talking about radio, we're talking about lowering or the loss of signal strength. Okay. So let's uh let's just look at an example attenuator here. An attenuator is a passive device. Well, could be we'll talk about that later. A passive device which reduces the power of a signal. Electrically, it's typically made from simple voltage divider networks. We'll talk about that more in a minute. Typically measured in decibels or dB of power reduction. A 3 dB attenuator reduces the power to 50% of the original signal. 6 dB reduces it to 25%. Attenuators can be added in series, in which case their dB rating is added together. So if you had a 10 dB attenuator and a 20 dB attenuator and you put them in series, it's just like having a 30 dB attenuator. Okay. Uh, that would give you a 30 dB would give you a loss or reduction of the power coming out will be 1,000th of the original power going in. Okay. And attenuators can be balanced or unbalanced. They're typically unbalanced for coax cable or balanced for like a twisted pair cable or something like that. We did have a class on balans or however you say it. And I unfortunately wasn't able to attend that week, but in that class, you kind of learned the difference between balanced and unbalanced networks, as we call them. And so you can build attenuators for balanced systems and for unbalanced systems. Let's talk about decibels for a minute, because decibels always confuse me. Okay. A decibel is a relative unit of measurement equal to 1/10 of a bell. Now, that's another one of those great definitions, right? Well, what the heck's a bell? Well, the bell is a unit of measure that was named after Alexander Graham Bell. For whatever reason, they dropped an L and they call it Bell with BEL. Normally, we don't talk about bells, we talk about decibels. And so you'll always hear people talk about dBs, not just Bs. Okay. So 1 decibel, deci is the SI prefix meaning 1/10. So it's 1/10 of a bell. And it represents the ratio between two values of power. Now, that wasn't supposed to still be in there. I don't know what the definition was. I've got to edit this page. Let's see if I can edit this. The bells inside the phones, yeah. Well, they used to have bells inside. I'll fix this later. Anyway, I did some. So I'm not a PowerPoint professional, okay? I'm a Unix guy, and I was looking at this thing and trying to figure out how do I put this formula in here? And I thought, well, there's a button on here that says convert from LaTeX format into math. And so I typed in my little formula in LaTeX format, and that first line there is what I got, which is pretty horrific. And so then I figured out there is a way to actually pick the different components off of a menu and fill in the values that you want. It was really painfully, it took me a long time to just make this little formula in PowerPoint. Now, it was very much easier to write it out in LaTeX form, but for whatever reason, PowerPoint didn't want to do the conversion for me. Anyway, if you look at this, the L is the loss, the P out and the P in are the power out and the power in. And so you divide the power out by the power in and then take the log of that. And then you take all of that and divide it by 2. And that gives you your decibels of loss. Okay. So you'll never have to see that again. You don't have to know what that means or anything, but that's the actual formula that's in use. And it's measured on a logarithmic scale. Does everybody understand a logarithmic scale? So if you don't, what a logarithmic scale is, if you've ever used a slide rule, it's got a logarithmic scale on it. And I was going to bring my slide rule tonight, but because of the traffic coming up from Lehigh, I didn't even stop at the house. I just came straight here. So I don't have that with me. I don't have a lot of things with me that I wanted to bring, but oh well, at least I'm here. The logarithmic scale, if you look at it drawn out, you're familiar with like a number line where you have 1, 2, 3, or like a ruler. If you were to look at a ruler, everything is the same distance apart. So 1 is the same distance apart as 2 is the same distance apart as 3, and so on, right? So if you had 10 inches, it's like 10 1-inch long pieces. A logarithmic scale compresses that down with a nonlinear function. And the way that it ends up working out is your first 10 fill in a certain amount of space. The next 10 take up the same amount of space as just one from the original one. And the next 10 after that take up a tenth of that second one. So a hundredth of the first one. So if you're looking at decibels, and remember, a decibel is a tenth of a bell. So if you're thinking about bells, 1 bell, 2 bells is going to be 10 times as much as 1 bell. 3 bells is going to be 100 times as much as 1 bell. 4 bells is going to be 1,000 times as much. Okay. This is how a logarithmic scale works. All right. So we measure bells and decibels in a logarithmic scale. Sorry, got to keep the vocal cords lubricated here. All right. So let's get to the next page. You'll hear other notations with decibels. You might hear of dBUs, dBVs, or dBIs. We use those in different contexts. A dBU is when you have this extra letter on, it's taken against a defined reference value. So instead of being the input power, it's a fixed value. Okay. And it's dependent on what the nature of the thing that you're measuring is. A dBU is based on 1 milliwatt and is usually referenced to a 50 ohm load, and it's used in electrical transmission essentially. And so you'll think about this. If you ever wonder why we want our antennas to be a 50 ohm resistance across them, that's why we do this, because all of our math is built around this 50 ohm difference, resistance or inductance or whatever it is. Not inductance. What is it? What am I thinking of? Impedance. And thanks, Paul. So if you ever worked with cable TV, that is 75 ohms. So it's different from the radio frequency stuff that we use. Okay. So if you've got a hunk of old cable TV coax, don't use that for your ham radio antenna because it's the wrong impedance on that cable. You want to get 50 ohm cable for amateur radio stuff. All right, dBV is relative or against 1 volt. And that it doesn't care what the impedance is, it's just against the voltage. Okay. And then dBi is the one that we will typically use when we're talking about antenna systems, and it's relative to a theoretical isotropic antenna. Does anybody know what an isotropic antenna is? An isotropic antenna is a theoretical antenna that radiates exactly equally in all directions. So you're not going to really find one of those in real life. I mean, you could maybe, well, it doesn't go in all directions, right? Yeah, I mean, it's basically if imagine if you could stick like a ball on the end of your coax and that ball was your antenna and it was radiating in all directions. That would be the closest you could really get to it. A rubber duck is really nothing better than a duck made out of rubber. I don't know, but hence the name, right? But yeah, so right, yeah, exactly. My favorite definitions. But an isotropic antenna would be a theoretical antenna that radiates equally in all directions. So your dBi is relative to that, okay? And dB are used to measure both loss and gain. So an antenna system, for example, the Yagi here that you want to hold that up for a second, that Stan has here, that is a gain antenna. So in the direction it's pointing, well, it used to, in the direction it's pointing, um, it will actually give you more power than what your antenna is being exposed to, right? It'll concentrate that. And when you're sending with a Yagi type antenna, you'll get a stronger signal than what you're putting into it. There's a certain amount of gain that comes with that antenna. Now, of course, there's only a certain amount of power. So where does that gain come from? It comes from making the signal more directional. Okay. So with the Yagi antenna, it's trying to focus almost all of the energy in one direction. So it can take all the energy that would be being thrown out all around you and focus it down into one direction. Think of it like a spotlight. If you've got a candle, that's putting out a certain amount of light. If you put a reflector behind it, now you're focusing that light. It's much brighter at the thing that you're pointing it at, right? Okay. And loss, it's also used to measure loss. And if you're talking about some long length of cable, different types of cable will have different amounts of loss per distance and per frequency. So that's another thing to think about. If you're looking at, well, I'm going to put up my HF antenna, what kind of cable do I want for that? Um, Maybe what, RG8 or something like that would be acceptable. But if you're putting up a microwave antenna, RG8 is going to have terrible loss on that frequency just because of the nature of that cable and how it's made. So you're going to want to use some kind of higher quality cable that is designed for that particular frequency that you're working with. And when you go to buy cable, they will typically have a chart that shows you what the frequency and loss rates are for different lengths of that cable. Usually they'll be like per 100 feet or something like that. So that's something to keep in mind when you're deciding what kind of cable you want to use for your feed line installation, depending on what bands you're going to be operating on. All right, let's get back to our attenuator. So why would we want to attenuate a signal? I was talking to a friend of mine at work today, and he said, "Well, what are you doing?" And I said, "I'm looking for a particular picture of an attenuator." And he says, "An attenuator? What's that?" And I said, "Well, it reduces signal strength." And he's like, "Why would you want to do that? Why would you ever want to reduce your signal strength? I mean, don't you want more strength in your signal? I mean, that's what we normally think of. Well, if your signal is too powerful, it might overwhelm your equipment. Okay. This is typically the case with very sensitive test equipment, like a signal analyzer or an oscilloscope. I was going to bring a tiny SA in, and like I say, I didn't stop at home to grab my stuff, so I didn't bring it. But a tiny SA is a little tiny box. It's about this big, and it has an input and an output, and you can use the output to calibrate it it'll actually generate a signal that you can pipe back into it and calibrate it so that it's measuring everything correctly. And you can feed a signal into that and see, like, across the spectrum where that signal is strong and where it's weak. And why would you want to do this? Well, when you have a snazzy Baofeng radio from 5 years ago or 10 years ago, those things were really noisy. They were not great. They would put out sometimes more power on their harmonic frequencies than it did on the frequency you were trying to transmit on. And the FCC requires that we don't do that because they don't want us interfering with other signals out there. So you can hook this up to your tiny SA and transmit on it and see, oh my gosh, this is how good my radio is, or this is how terrible my radio is. And if it's terrible, huck it in the bin. Yes, Logan. It reduces the power of it. So the signal is going to go forever. Okay. When you transmit, that signal is going to go forever. But the farther it gets from the source, the lower the power that it has, right? The more power is used up as it goes along. So if you have more power, you're able to get your signal to be received farther away. Does that make sense?
Yes. That we use for camping if we hike very far.
You're thinking of a repeater.
Oh, that's a totally different thing. That's a totally different animal, right? Okay.
That's way around. That's making your signal.
Yeah, that's making your signal go farther than it would normally, right? We'll talk about why we want to use an attenuator coming up here, okay? So in our test environment, the tiny SA is a great little gadget, but if you give it more than like what 10 milliwatts, that thing is going to just melt. Okay. So you don't want to pump even 5 watts from your handheld into that thing. Definitely you don't want to pump 100 watts from your HF radio into that thing, right? Because it'll just turn into garbage. You'll fry it. And so you would want to put an attenuator in place to reduce the strength of your transmitted signal to something that the tiny SA can handle, or your oscilloscope, or whatever test equipment you're using. Okay, so that's one reason why we might use it. And another reason we might use it is if we're attempting to locate the source of a signal. A strong signal will appear to be coming from every direction at once. Okay, so if I'm close to a transmitter, I can't really tell where it is by moving my Yagi antenna around and pointing at it because it's picking up that strong signal no matter where I point it. Okay. The Yagi is great when I'm a mile away from it and I can say, oh, I hear nothing. Oh, there it is. Well, now I hear nothing again. So it's got to be in that direction, right? If I'm trying to locate a transmitter, the Yagi is great for picking those initial bearings to line up on it. But once I get close to it, it's just too powerful. I can't use that Yagi anymore. And so some people will like take the antenna off their radio completely and hold it against their body and let their body absorb the radio waves coming from behind them. And they'll turn around until they can hear the sound, and then it should be right in front of them, right? That's not great. But with an attenuator, I can combine an attenuator with my Yagi and still maintain my very directional capability of the antenna, but reduce the signal enough that I can still hear the difference as I move around it. Yes. This type of antenna that Stan has right here is a Yagi antenna.
Just tripping over the backyard.
So our class last month actually was on the Yagi UDA antenna, and we'll probably be building some this coming year. So
Reflector
and driven element, yeah. Okay, so this reduction of source of a signal is usually encountered when we're doing fox hunting or signal triangulation. Okay, let's continue. So how do you make an attenuator? Well, there's a couple of different types of circuits used in attenuators. Some examples are pi pads And if you're familiar with the number pi, there's this is, let me see if I can do this. This is the symbol pi, and you'll notice this looks almost like the pi shape, the shape of the pi letter, right? Don't look at this one over here. But this one definitely looks like the pi shape. And then there's what they call a T pad, and you can see that one looks like a T. Now, in this example, these ones on the left are for unbalanced circuits. And these ones on the right are for balanced circuits. And you'll notice that they do a little bit of extra connectivity here to make sure that the circuit stays balanced or on this one, that they don't do on this one, okay? And if you look at these symbols here, this is like the input to the thing, and this is the output. And then this is a resistor here. This is the ground. So these are tied to ground. And we run our power through here, and it will bleed off some of our power to ground. And so the power that ends up coming out is attenuated or reduced based on the amounts of these resistors. And there's a chart, a table you can go through, or a calculation to figure out what resistance you want for the amount of attenuation you want. Yes, Russ, you got your hand up.
This symbol in both of those is identical, isn't it?
Which is the second symbol?
The one on the right.
So over here,
Yep.
we have, this is resistor, I can't really see it here. This is resistor S, and this is resistor T. This is P1, and this is P2. And then you've got Z1 and Z2, and I don't remember what the Z's are. I think that refers to
Impedance, yeah.
impedance, yeah.
Are you saying the one that directly below is identical?
This one here is identical to this one. Yeah, I think they are. And that, I don't know if that's me copying and pasting the wrong one or if they actually were identical. I'll have to look at my source.
So are they used in conjunction with the first one?
No.
No,
The ones on the left would be used for a coax
yeah,
unbalanced.
these would be used for coax. These would be used for like twisted pair or something like that. A balanced cable, yeah.
One that has two parallel conductors,
Okay.
and neither of them fit ground.
So I will double check my source and see if I pasted the wrong diagram in here. I was kind of putting this together in a hurry and I may have messed that up. So I'll confirm that before I publish this. Now let's talk about some specific attenuators. And I happen to have a couple here that Dan let me borrow. I don't have the one that I had at home that I was going to bring, but oh well, this is what you've got. So Dan built this one here. And as you look at it, I'm going to pass it around, but it's got an antenna in connection here and an antenna out connection on this side. It's got a bunch of little toggle switches, and the top it says off, and at the bottom it says -1 dB, -2 dB, -3 dB, -5 dB, -10 dB, -20 dB, -30 dB, -40 dB. And so he's got a total of -111 dB. So it's negative, so it's reducing the signal strength, right? Remember, we said we could either increase it with gain or we can reduce it. And attenuators are all about reducing, right? So if I wanted to have, say, 7 dB of reduction, I could turn on the 5 and the 2, and now I've got 7 dB because you add those numbers together, okay? Dan asked me not to open it up because it's kind of fragile inside, but I'll pass it around so everybody can take a look at it. And I actually have a picture of the inside. So we'll go to the next slide and look at that. But basically, this is a completely passive device. There's no power involved in there. You hook up your antenna cable on one end, you hook your radio up on the other end, you dial in the attenuation that you want, and there you have it. And so when you're using this in a fox hunt, for example, as you get closer to the fox, you want more attenuation. So you flip on another switch and increase your attenuation. It's all resistive, exactly. So this is the inside of the box, and you can see he's identified them here. This is the -1, this is the -2. These are the switches, right? And then he's got the resistors, and they're built in that pie shape. These are those pie pad type resistors setups. And he's actually got this document which says what the resistance is for each resistor. He's got it all calculated out so that you can see what he had to do to design and build this thing. So if you guys want to look at that after, this is a good diagram here because it shows specifically how the resistors fit into where the switches are and everything. So it's more like a schematic. They have different values. They're the same kind of resistor, but they have different values. And so when you look at this sheet, for example, you'll be able to see the color bands that were on each individual resistor. And so you'll be able to see, yes, Dan.
Those are about half watt. So that kind of limits the power.
That limits the amount of power, but remember, for fox hunting, it's receive only.
Yeah.
So the power coming in is minimal. It's not a large amount of power coming in from the signal, even with your Yagi. And if you're standing right next to the fox is putting out maybe 1 watt to 5 watts. It's not going to overwhelm your resistors, right? So that's the switched attenuator that Dan put together. It's pretty cool. There's also what we call, what's that?
So me into the 3D print.
Yeah, right. I mean, it's very easy to put one of those together. You just have to be careful not to short things out, make sure everything goes in the right place and you're good to go, right? So the other thing that's used in fox hunting is what's called an offset attenuator. And this is an active device, so it actually requires power to work, okay? What it does is it mixes a small offset signal with the incoming signal, and that essentially causes the signal to move away from the original frequency. And you've got one, yeah. So this is an example of a fox hunt attenuator. And the idea is I turn this thing on. And I see the little red light comes on. It's got a battery inside. And then I can dial in the amount of attenuation I want from minimum all the way up to maximum. And then I tune my radio. This one, it doesn't say what frequency offset it is. Usually they're about, 400 kilocycles or something like that, maybe 0.4 of a megahertz. I don't know. Paul, do you know what's typical for these?
I don't, but, you can select it.
You can calculate it based on what you put inside here, right?
The farther you get from the original signal frequency, the less likely you'll get overload from the fox itself.
Right.
Leading through.
Right. So I'll pass this one around too. Now, there's a guy down in Utah County, Noji. Anybody know Noji? Quite a few people do. So Noji actually put together a plan on how to build one of these. And so we may build one of these in a meeting as well, because it doesn't take much to put it together. But this is Noji's offset attenuator, and it's got you can't see the jack on the other side, but you can hook up your antenna on one side, and then on the other side you put your radio, and you can see what he's got in here. There's a variable resistor here. That's the little dial, the pot on top, that you use to select how much signal is going to come through. And then you tune this. This has got a 4 megahertz crystal in it. So it's going to mix a 4 megahertz signal in with the original, and you're going to be 4 megahertz off. So if your Fox is at 140, say 144.5, then you would tune in 4 megahertz away from that to pick up the attenuated signal.
In either direction.
In either direction, above or below. Okay. And remember, since you're just receiving, it doesn't matter if you're outside the band when you do that, which you will be. But since you're only receiving, you don't want to transmit through one of these things or you'll ruin it. But you can set this up so that you can actually tune into that a little bit off from the Fox. And then if you get out to where you're finding, oh, geez, I can't find my Fox anymore, just switch back to the main frequency. It's that frequency is still coming through. Switch back to the main frequency, and then you can locate it again with your Yagi. So that's a pretty simple circuit design. You put that together in an hour and drop it into one of these kit boxes, and you're ready to roll. He's got it 9-volt battery powered. There's the power switch there. It's got the crystal and the signal generator. There's a capacitor there. There's a variable resistor, and then a couple other resistors and a diode, a couple more capacitors. Not much goes into this thing. It's pretty simple. And he's actually on his website, he's got the circuit board that you can put together so you can use a kit build circuit board, put the components together, solder it all together, connect wires between the pieces where they need to go. Good to go, ready to roll.
Yeah.
Yes.
The idea that you're trying to mix the two signals to get the sum and the difference, and then you're tuning for a difference.
Correct. Yeah. Logan, you got another question?
0, 7, J,
So this is a capacitor. It's capacitor number 3. This is 0.0047 microfarads. This character right here is called a mu, and it means micro. It means 1/1,000,000th. So a millionth of a farad of capacitance is what this one is.
how many are
There's one of these, and then there's 2 up here. These are 470 picofarads. So interestingly enough, 470 picofarads is the same as 0.0047 microfarads, isn't it? Or am I off by?
Nanos.
I'm off by a factor of 1,000, right? So pico is much smaller. So these are like 1,000 times. These are like 1,000,000 times less than this one. No, these are 1,000 times less than this one.
Right.
Because this would be 470 nanofarads, right? Oh, okay, 4,000 is my terrible.
That's going to be 4.7 nano.
4.7 nano. Thanks, Justin. Logan, you had another question.
the,
And this one?
yeah,
Okay, so this is completely passive. You don't need any power with this. And the signal is coming straight through. So you're going, you tune your receiver to the same frequency that you're looking for. It's going to reduce the strength of that signal. What this one does is it actually takes that strong signal and peels off a part of it and puts it on a different frequency at a lower level. So then you tune your radio to that other frequency, and then you can adjust how much power is making it through on that frequency with the dial. And it requires power to do that.
It looks like there's very little of tuned circuit, there's no real tuned circuit on the output of that thing.
Right.
So you could probably go any multiple of 4 megahertz.
Yes. And get lower and lower and lower as you
So
went.
the signal's at 144, you can get it at 148, 152,
Yeah.
156, and the farther you move away from it.
The more attenuation you're getting on a logarithmic scale, right? So, yeah.
6 dB per octave.
Hmm.
well, what's the difference with it, with power and the difference between with it?
It requires power to run this circuit. Okay.
The other one doesn't power to.
Well, there's power that comes into it with the radio signal. So it's running strictly off of the power of the radio signal. Yeah, so this is an active device, whereas this other one is a passive device. So I don't need to put any additional power in there. I'm just working with the power of the radio signal. But with this one, I'm taking the power in at the power of the radio signal and I'm mixing it with another signal. So I have to power that generator for the other signal to give it enough oomph to do its thing. And then I combine those two together and it comes out the other side, right? Now, the other type of attenuator that you may encounter is what's called a fixed reduction attenuator. And these are basically, this one here is what I was going to bring from home, which I failed to stop and grab. But basically, you just put this in line and it gives you a fixed amount of attenuation. I think this one is about 30 dB. This one is 100 dB, I think. And this one is like 10 dB. So there's basically just one of those little resistor circuits inside there that does its thing. And you can see it's got like a big heat sink on it. That's because when you put a lot of power through something like this, it tends to make your resistors get hot. And so you need to let that heat out somehow. These would handle a driven circuit. So if I was going to put my handheld on my tiny SA, remember we were talking about doing that? I would want to put one of these in between there that can handle the power that's coming out of my tiny SA. I wouldn't want to use Dan's little gizmo there because it's not going to handle the power that I would be wanting to put through coming out of my radio. Okay. So I would use something like this for that.
Somebody was asking, how are these powered? These things are essentially just dumping the power from your signal as heat. They're
Yes.
turning power from your signal into
They're
heat.
powered by your signal and they turn it into
Yeah.
heat. Exactly.
And that's why some of these higher power ones tend to have big heat sinks.
They have big heat sinks on them
A
to
lot of
dissipate
power
that heat.
makes a lot of heat, and you got to get rid of that heat.
Yep, you got to get rid of the heat. Otherwise, your stuff's going to melt, and you don't want that.
And this is just a slight variation from a dummy lid,
Correct.
which is an
An attenuator with no output, right? That was the other thing I was going to bring was a dummy load so you could see the difference between them. Basically, if I grab one of these things and it has one connector on it, there's no connector on this side, that's a dummy load. And why would I want to use that? Well, I would use that if I'm testing like the power of my radio, but I don't want to be transmitting all over the place with it. I would run my radio into my power meter and then coming out of the power meter, I'd go into a dummy load. And then that dummy load is going to dissipate all of the power of my signal, almost all of it. There will be some leakage, right? But probably 99.99% of my signal would get turned into heat. And the dummy load will handle that. I've seen, used to be in the Heathkit catalog, you'd see this dummy load that was in like a paint can.
The heat pit antenna.
Yeah, the cantenna, right? And you could dump 100 watts into that thing pretty much all day long and it wouldn't overheat. It was full of oil and the, the the can held about a gallon of oil and it would take care of that heat for you.
They were rated at 1.5 kilowatts for, I think, 2 minutes or something.
Yeah. So yeah, if you had a big amplifier, you could pour all kinds of power into that thing.
And up until the early 70s, they were filled with polychlorinated PCB oil.
Some toxic materials, yes. Logan, you have another question? Yes, if I put too much power into it, like this one is probably rated for, I don't know, I want to say 10 watts. If I tried to dump 100 watts into that, it would probably damage it.
And there's usually a chart that comes with them that shows.
That says what you can do with it,
that
yeah.
shows power level and for how much time. So that one on the bottom can probably take 100 watts for 60 seconds. Or 5 watts for indefinite.
For as long as I want to pump it in there, right? Yeah.
One up in the corner would be like something you hook to your handheld radio that we pack around. Where that other one would be something like we hook to the mobile like Cadence truck. It's 50 watts.
You okay?
5 watts for the handheld, 50 watts for the mobile. So you've got to select the right dummy loaders and attenuator for your problem.
All right, so this is what I was looking for when my friend looked over my shoulder and said, "What the heck are you looking at there?" And I was looking for examples showing somebody using an attenuator with some kind of test equipment. And unfortunately, I found lots of pictures of oscilloscopes and tiny SAs and lots of pictures of attenuators, but no pictures of the two of them together. So I found this one. I think it was from a YouTube presentation or something like that. He's got this little gizmo here, which I assume is some kind of interface device that converts the signals into something that can be shown on the computer. And he's got his attenuator on here, and then the signal comes in this way, it goes through the attenuator and into this device. And then an example with the active attenuator, this guy has one attached to his Yagi antenna, and so he can easily dial in the amount of attenuation he wants, set his radio to one of those offset frequencies, and wave his Yagi around as he gets closer and closer to the Fox. He can turn that up.
Looks like it's probably using the same schematic as Noji.
It's most likely exactly the same, yeah. Because in fact, it says on here 4 megahertz offset. And then he's got max attenuation and min attenuation. Antenna on this end, radio on this end, he's got a 9-volt battery taped to the side. So yeah, it's probably the exact same circuit.
Yeah.
All right. That's all I've got. It's like I said, it's a very attenuated program tonight. So if you guys have any questions or comments, if you want to see Stan's Yagi, if you want to fiddle with the attenuators that are Dan's, he asked me not to open that one up because he doesn't want anything getting damaged, but he did say if I was doing it, it would be okay, but I probably shouldn't do that. Other questions? Stan, you had a question.
Oh,
Or comment.
You know, the load, you know, that they could use on a transmitter, because you never want to run your transmitter without a load.
Right. You either want an antenna hooked up to it or you want a dummy load of some kind to pump that power into. You don't want that power just going out and coming bouncing right back into your transmitter, or it'll fry your finals on your amplifier, right? So that's why we would have a dummy load. Logan, another question.
Like, or signal, or there's no such thing.
So the heat is a byproduct.
Yeah, heat. So you need to learn about this concept called entropy. And it's probably too deep to go into for somebody of your age at this stage. But the basic rule is in the universe, entropy always wants to increase. Entropy is like the randomness of stuff. And so everything wants to become more random. And in doing so, it usually ends up as heat. Okay. Heat is like the most random that you can get. And when you are trying to go the other direction, you have to take extreme efforts to make that happen. So, for example, you got a refrigerator at home, right? And a freezer. And the freezer compartment is cold, but outside the freezer, it's not cold. So if you think about how does that happen? How do I get the heat out of the freezer and outside of the refrigerator? Well, I have to use power to do that. And the interesting fact is I have to use more power to move the heat out of there than it would take to generate the same amount of heat. So if I want to get that thing to become cold, I have to use energy to do that. If I want to increase the signal coming out of my radio, decreasing it, I can turn it into heat. No big deal. That's what the attenuator does. If I want to increase it, I've got to pump power into it and use an amplifier to turn it into a stronger signal. So the reverse of attenuation is amplification. Does that make sense to you? A little? When you get into junior high physics, they'll talk about this kind of stuff, and you'll be like, I already know how that works. So you'll really impress them. But anyway, other questions or comments?
There is another technique you can use in fox hunting that uses nature's attenuation. And that is if there's a fox on 144 megahertz.
You can go to a harmonic of that.
And the harmonics, for many radios, the better quality Japanese radios are usually minus 60 dB on the second harmonic and then lower from there.
Yeah. Now, if your Fox is using one of those old Baofengs, then your all bets are off, right? Yeah.
You have to go up several bands to find the weaker signal.
Right. And hopefully your radio will handle those other bands up much higher, so.
Yeah, but I've got, this handle will go to, 1300 megahertz. So I can go to the, fifth, seventh harmonic of 2 meters. And, is that right? Yeah. I think up to the eighth harmonic. And what I found, at the digital conference last year in February was that the Fox they were using actually seemed to have more output up there than it did on 2 meters.
So Paul brings out that, yes, you can also take advantage of the harmonic nature of the radio transmission and tune into one of the harmonics that are significantly far away from the original signal if your equipment will handle receiving that far away. And he points out that his nifty Quansheng radio can go up to 1300 megahertz, which, oh, that's an Alinco? Oh, I've got the Quansheng and it'll do that too. So, but yeah, so you can actually tune into one of the higher harmonics. Of course, you have to calculate the frequency that you want to be tuning in on.
If you've done the math to figure out the log of PI over P over.
Sure, you can do that math, right? Yeah, so, but yeah, so that's another option for fox hunting. And we'll probably talk more about fox hunting. We'll probably build some Yagi antennas. We'll build some attenuators, and maybe we'll build a fox and we'll go do some fox hunting. Maybe in the summertime when it's not cold outside. But I know Taylorsville does a fox hunt every month, and they put a couple of transmitters out in park over there off of 22nd West.
They're doing one in January.
Oh, they're doing one on the 220 band. So that's another interesting point as you talk about that. Most foxes, when you do a fox hunt, most of them are going to be on the 2 meter band, and that active attenuator works great on the 2 meter band, but it's not going to work on the 220 or the 440 band. That passive one will work perfectly. I mean, I guess technically it would work, but it's going to be way outside your band. So you probably are not going to have equipment that would receive that offset.
220 down to 140 is, well, 78 or 80 megahertz.
Yeah.
So you could tune to the top of 2 meters
Boom.
and be 76 off, which would be, what's 76 divided by 4?
9.5,
Okay.
9.25.
So, yeah, that would be nine harmonics of 4 megahertz away from the 220 frequency.
Yeah.
So that would knock it down pretty good.
So yeah,
Yeah, maybe knock it down too much.
too much, right? Yeah. All right. If there are no, yes,
The director and the reflector are all electrically all one piece,
correct.
but this one is split.
Is a dipole, right?
And if you want, I can pass that up, they can see. Split.
Now, when you use that, do you have a balancer between the two sides?
Well, I've not finished building this, I still have to put the UHF connector in there, and then the little, what he called the hairpin.
Yeah, the hairpin.
I've still got to do that.
Okay.
I'm hoping Dan will be there.
Dan is busy helping out Santa Claus pretty much every night this month. So don't be surprised if we don't see him again until next month.
Still next year.
Yeah. Logan. Which one do you want?
Hello, I'm at a meeting. Hey, I'm at a meeting. I'll call you back, okay?
Stop.
Yeah.
This one?
No, go back. Go forward again. Stop.
What does isotopic attain, so in DBI nearly is?
So isotropic antenna, that is a theoretical antenna that radiates power in all directions equally. So any normal antenna is going to have some kind of pattern that it's going to radiate power on. So like on Sherwood's rubber duck on his radio, it's going to come out more to the sides than it does straight up. Okay. With this Yagi antenna, if I'm transmitting, it would come out more in one specific direction, the direction you're pointing it, right? An isotropic antenna, it would come out in all directions like a sphere, right? A spherical signal, all equally everywhere around. And the reason we call that theoretical is because it would be really hard to actually build something that did that. So, all right, I'm going to stop the recording. Thanks, everybody. And we will get this on the website as soon as I can.